Good morning, everyone. We decided to get all this information out there about these recursive relations. And I know in 3 days in a row I posted a very quick introduction video. I then yesterday posted hopefully something more specific about the big variety of recursive relations you can solve. But really the way we went about solving them was a little bit more of looking for patterns. Once we hopefully would see a pattern, came up with a conjecture for A sub n, or the closed form or the general form. And then we could prove it by mathematical induction if needed. Well, today we're going to take a look at a very specific method for solving a very specific type. And in terms of the IB world, and quite honestly, this can be used to solve a lot of different types of situations. It's something worthwhile looking at. Again, continue to read through the sections, B1, 2, 3, and 4, study some of the investigations and examples. And then hopefully if you end up with one of these recursive relations when you're trying to solve a problem, you can then hopefully solve it or get the closed form. Now, the specific type is that second degree, linear, homogeneous with constant coefficients. Second degree, remember, that means it's going to use two previous terms. Linear, nothing is being squared. I'm not taking one of these terms and squaring it, cubing it, or anything like that. Homogeneous, I don't have another function added to it like n squared or plus n. And of course constant coefficients. I don't want those to also be variables. That would be a problem. The method for this comes down to really something that's called either the auxiliary or characteristic equation. That's probably the most common, but the characteristic equation. So we're basically going to be taking this equation and transforming it into really a quadratic. And we could use r, we could use x. It's very common to use lambda in our text, so I'm going to use a combination. First, I'm going to use r. Since this is an n minus 1, and n minus 2, this basically becomes the constant. This is going to become r, and that's going to become r squared. Now, there's a lot of theory or procedure as to why we want to choose that, but I don't want to get into the proof and derivation of some of these things. So the characteristic equation that I'm going to use is going to be r squared minus 3r plus 2. Then I'm going to find the solutions to that equation. Of course, that's just r minus 2, r minus 1. So r is going to be 2 or 1. So getting the characteristic equation is part of it. The second thing is to recognize and understand, even with some we've already done, is that geometric sequences or geometric functions are very common and very popular. It's also worth to note that for any specific type of a recursive relation, the closed form is not unique. It means you could come up with a couple different closed forms that could possibly still work. So what we want to realize is that since geometric functions are so common and prevalent with this, or somehow connected, we're just going to say it's going to be a combination of some geometrics. So I am going to let my closed form be some coefficient, I'll call it C1 for now, times one of these, I'll use the 1 to the nth power, plus a different coefficient using the other root to the nth power. So there's my closed form. But of course I would love to know C1 and C2. And that's where this information comes into play. If I'm looking at the zero term, I get 2. So because of that, I get, where do I want to write it? I'll write it over here. I get 2 is going to be C1, 1 to the 0 power, which is just 1, plus C2 times 2 to the 0 power, which is just 1. So that's one equation. Now I'm going to use this one. 3 should be a sub 1, which is going to be, again, just C1 if I put a 1 1 there. And if I put a 1 here, I get 2C2. Well, if I subtract these two equations, I get C2 to be 1, and actually C1 to be 1. So now my solution, or my closed form, is going to be C1, which is 1 times 1 to the n, plus C2, which is 1 times 2 to the n. Now we can simplify this even further, because that's all just 1. So that's my nth term. Now, possibly, or maybe even probably, if I would have just expanded some of these, I might have noticed that anyway. For example, there's my first term, which is 2. Second term is 3. Now my third term, if I solve for a sub n here, my third term is going to be twice the second term, or sorry, 3 times the second term, so that's 9, minus twice the term before. And you start to notice that if I take 2 to the first, there's maybe 0 plus 1, I'm going to get this term. 2 to the first plus 1, I'm going to get this term. 2 squared plus 1, I'll get this term. So I might have noticed this anyway. Next one's going to be 9, 2 cubed plus 1. Okay? But this is a more foolproof way to get that. Now, the other two examples I'm not going to complete, but I'm going to set them up, because what happens is everything's the same except what happens when we solve that quadratic. So let's take a look at this one. Here we have this quadratic, or this recursive relation. Shouldn't have it equal 0 yet, by the way. Yeah, I guess I do. Never mind. So if I go ahead and write the characteristic equation for that, I'm going to use lambda. The book uses lambda quite often. Minus 2 lambda minus 2 lambda squared. Or sorry, just 2. And I have some of the solutions for this one already. But basically, lambda is going to be 1 plus or minus radical 3. So in other words, we didn't get two nice rational numbers. We got an irrational number. But then the work is the same thing. My nth term is going to be some constant times one of these to the n plus another constant times the other one to the n. You could then make use of your initial conditions. 1 equals C1, all of this to the 0 power, plus C2 times all of this to the 0 power, and then go from there. And ultimately, you're going to end up with something that just looks a little more complicated. 1/2 plus 1 over radical 3. 1 plus radical 3 to the n. Next one's going to be 1/2 minus. That would be minus. So that would be my nth term, my closed end form. So even if I start this, I got 1 and 3, and then I go to the next one, and the next one, and the next one. If I want to get to the 15th term without going through the first 14, I can just put a 15 into this end position, and that would be my answer. And it might be surprising that it's going to come out to a nice whole number, because everything here, we're going to have whole numbers. And you can play with that and see what happens after you go from 1 to 3, and then for the next one. All right, now the final example takes care of the other situation. In one situation, we have the quadratic lead to nice rational solutions. Here, we have the quadratic leads to irrational solutions. The other situation is going to be when the quadratic leads to a double root and how we deal with that. Now you might be thinking, what if it's irrational or not irrational? What if it's imaginary? Well, we're not going there. So let's just see what happens. This is a little bit different format. Okay, so if I just go ahead and replace, this is my highest kind of value for n. So that's going to be your n squared, your lambda squared. So here I'd have lambda squared. That's just going to be 6 lambda minus 9. So if I change that and set it equal to 0, I get my characteristic equation. Solving that characteristic equation, it is a perfect square. So I get lambda to be 3. Now, what am I going to do then if I only have one of those roots? Well, it's not that big a deal. We just make a little bit of an adjustment. I'm going to let now a sub n be a linear c1 plus c2n times that root to the nth power. So it still has a geometric piece to it, but the coefficient is going to allow for the two variables, and we want to make it a linear. And then if we go through that work, takes a little bit of time, we are going to end up with the nth term be 2 minus 4/3 n times 3 to the n. So in this very last one, let's actually expand this just a little bit. We know that 2 and 2 are the first two terms. Okay. The next term is going to be 6 the previous minus 9 twice the previous. So 6 of these minus 9 of these. So 6 of these is 12 minus 9 of these. I think I get negative 6. And then for the next term, I'm going to get 6 of these minus 9 of these. 6 of these, negative 36 minus 18, negative 54. If I then go ahead and take 6 of these minus 9 of those, I'm going to get another number, and so on and so on. So here was 0, 1, 2, 3. The big question is, if I put a 3 here, do I actually get negative 54? Well, if I do that, I get 3 to the third, which is 27. 4/3 times 3 is negative 4. 2 minus 4 is negative 2 times 27 is negative 54. Now, that doesn't prove it, but basically what we've done already proved it. But it's just a way to make sure that this weird-looking nth term expression is always going to match up with the appropriate term in that recursive or in that sequence. So that's basically it on recursive relations. I am going to post a short worksheet. Please let me know if there's any questions. I can have another video early next week, over the weekend, tomorrow, anytime, if you want to see more of this. But good luck, and stay in touch, and we'll be back next week.